I'll be covering a topic on ramjet engines. So before moving into a ramjet, so we should um, just need to brush up a little bit on energy equation that comes usually in your gas dynamics or basics of fluid mechanics or aerodynamics courses. That's where the you will be introduced to this part. So usually in jet propulsion cycle analysis, not just ramjet, any cycle analysis, we usually use the idea of stagnation properties, right? So you guys are aware of it, right? Like, can anybody tell me what is a stagnation temperature, say? Yes? Yeah, anybody can just tell me what is a stagnation temperature is all about? Temperature measured at the stagnation point. No, my question is exactly about what is the stagnation point, right? So temperature is just an example I have taken. It can be any properties. Like, usually how do you define a stagnation temperature? When the local velocity in one direction is 0. Okay. Yeah. So usually what I observe is even in textbooks, what you guys are going to read is perhaps this particular definition of stagnation temperature. A stagnation temperature is a temperature when a flow comes to rest adiabatically or isentropically, right? So am I right? So this is the kind of definition you might have read or you have been introduced to. Yes or no? Say like a flow, we have a flow, so that comes to rest adiabatically to some point where velocity becomes 0. So the temperature measured at that point, you would call it as a stagnation temperature, right? This is a right definition with less information, what I say. So you have to catch this concept very clearly. So whenever a textbook or whenever this kind of definition is written somewhere, the inherent assumptions they impose is like it is a steady flow, the foremost assumption, and it is an inviscid, right? So these are the hidden assumptions which they don't mention in a first place. And there are some more assumptions also, like there is no body force involved. Okay, and you are measuring on a given streamline, so that is also important. So these are the hidden assumptions they don't mention. So we will define the stagnation temperature more thoroughly. So let me take uh, energy equation. This is just out of curiosity. Does anybody knows what form of energy equation is this one? Whether it's an integral or differential? Can you guys able to recognize it? The the equation which I am showing on the screen. Yes. Come on, this is very simple. You should be able to recognize straight away. The next question I am going to ask might be a little bit tricky, but whether it is an integral form or differential form, you should be able to recognize straight away. Yes. Do you find any kind of integral over a volume or area like that in this equation? No, right? You find a differential form. So it is a differentiated with respect to time over here. This operator is again like it's a well-known vector operator del. So which is again a vector operator. So this is again a, I'm writing it in Cartesian coordinate. This is also a differential operator, right? Right. So this is a differential form of energy equation. I'm not going to ask whether it's a conservative form or non-conservative form. You might not been introduced to different forms of governing equations, but let us leave at that point. But maybe in your actual classes, you will be introduced to all those terminologies, classification. And looking at this particular form of energy equation, can you guys tell me what are the assumptions it's already involved? This is not a full energy equation. I will give you a straight away. This is a reduced form of energy equation. So just looking at this equation, can you guys straight away tell me what are the assumptions involved in this particular form of energy equation? Remember, energy is a body force. So like it's applied over a volume. Yes. So it is involved with no body forces. Very good observation. Then adiabatic. Very, very good observation. Devnathan, how do you decide that it's an adiabatic? There is no heat transfer. Okay. Yeah. So there is no heat term, right? So that means like there is no heat generation or there is no heat addition in this particular form of energy equation. So it's clearly an adiabatic form. And do you find any dissipative term here? Yes. Do you guys find any dissipation involved in this particular form of equation? No, right? You don't find any viscous terms, right, in this equation. Viscosity is not involved in this form of energy equation. So there is no dissipation also. So it is an inviscid form of energy equation. So these are the assumptions you can straight away make out of given equation. Is it a steady equation? No, right? So still we are dealing with a time derivative term. So maybe it is in the total derivative term. So it involves both local plus convective, but still it involves a time derivative. So in that sense, it is not a steady state energy equation, but it's an energy equation with adiabatic and inviscid and no body forces involved. Clear? So this is the form of the energy equation we are going to take to define the concept of the stagnation temperature. Okay. So the right hand side, what you see here, it is an vector operator. Uh, can you guys just tell me what operator is this one when you are applying to this kind of term? Dot product. So when you apply a del operator with the dot product, what do you call that in your math? Just let me know whether you call it as the gradient operator or divergence operator or the curl operator. What do you call this? Yes. I thought you guys already went through your math courses, at least in your graduate level math courses. There you have been introduced to vector calculus. This is a divergence operator, right? When you have a dot product with any vector inside. So that means it's a divergence operator, right? So the property of divergence operator is such that when you apply a divergence operator on any tensor, you can apply to any tensor, you cannot apply to a scalar. So any tensor, so the order of tensor reduces, right? So the divergence of a vector is a scalar. That's what you studied at least in your math courses. So in general, you can apply to high dimensional tensor also, like you can apply to second order tensor, that is like a stress tensor like kind of thing. When you apply a divergence on a stress tensor, you get a vector. When you apply a divergence on a vector, you get a scalar. So that is how the order reduces. Whereas the gradient operator, when you apply a gradient operator on a scalar like rho, so it increases to like next order tensor. That means, so the scalar becomes vector, the vector becomes the second order tensor, like that. Okay, so that is the property of this operator. Whereas the curl operator, when you apply it on a vector, so it stays as a vector, so the order does not change. So these are the properties of these vector operators you should know from your basic mathematics courses. Okay, so in this scenario, I have a pressure that is a scalar field, the velocity that is a vector field. So how do you deal with this? So this operator is applied on a scalar multiplied to the vector. How do you deal with this? So can I write like this? Is it a correct way? I'm just taking that scalar out and I'm applying divergence of a vector. Is it correct or not? Yes? What do you think? Just let me know who are all thinks this is correct. So I can take the scalar out and rewrite in this form. How many of you think this is correct? Just put Y or S, whatever you feel. Okay, so like I don't want to spend too much time over here, so I thought like we can go into the details. So sorry. Okay. So this is a vector relation. Remember, pressure, though it is a scalar, but it is not a constant. This is a scalar field. Still, the pressure can be a function of x, y, z, and time, right? So this is an operator. Remember, this is an operator where you have to apply this differential operator on this scalar field. So you cannot simply take this scalar outside the operator and convert it into this form. It is not correct. So how do you deal with this type of relation is you apply a very well known vector operator relations. So that is whenever you have a scalar multiplying a vector and the divergence operator is applied on it, so it becomes like P the scalar times a divergence of a vector plus vector dotted with a gradient of a scalar. So this is how it becomes. Clear? So I am just expanding this term. Okay. So now I am also taking one more term, that is I am taking a total derivative of P by rho. This is a simple chain rule, sorry, U by V rule in differential form. So you can easily write, right, how d by dt of P by rho is, that is 1 over rho square times rho times dP by dt minus P times d rho by dt. Straightforward. There is one rho and one rho that cancels, and if I divide this rho to individual terms, it becomes this rho and this rho cancels, it becomes dP by dt and P by rho times d rho by dt. Clear? So straightforward. Now let me call this as equation 1 and this as equation 2. Fine. So next what we have is a continuity equation, that is another governing equation. We will take the help of continuity equation in the differential form. So differential form of a continuity equation looks like this. So again, I am not going into the details, but in actual classes, we are going to deal with this detailed discussion of conservative, non-conservative forms of equations and all. So now it is just a continuity equation. We will take it as a granted. D rho by dt plus rho times divergence of a velocity is equal to 0. Very straightforward. I can also like write this equation in if I want, I can also convert it into just equal to 0. That's also fine. So it's just an expanded form. Okay. So now I'm taking the help of continuity equation because, so if I club the this equation, so this one we already have dP by dt minus P by rho times d rho by dt, right? Where it is, yeah, here. So dP by dt minus P by rho times d rho by dt. And what is d rho by dt? So I can write d rho by dt is equal to minus rho times grad dot v. So I am just replacing over here. So if I replace that one, so what it becomes? I already have minus P by rho times d rho by dt is minus rho times divergence of a velocity vector. So one rho and one rho get cancels, minus times minus, that becomes plus. So that becomes P times divergence of velocity. Clear? And this is a total derivative of pressure. So we know any total derivative can be written as local derivative plus the convective form, right? So that means velocity dotted with a gradient of a variable. So that's what I am applying here, dou p by dou t plus the convection of the scalar. So now, can you recall? So what is this term is v dot del p times p times del dot v. That is nothing but this, right? That is a divergence of PV, right? This one, this entire term. So I can either write it as divergence of PV, something like that, right? Are you guys following? Good. So now, so this equation 2 is reformed into this shape. So let me still treat this as equation 2. So now I have equation 2 and equation 1. Let me club those two. Okay. So if I club these two equations, so the first equation I have rho times d by dt of E plus V square by 2. This entire term is a scalar. It's an energy, right? Internal energy plus kinetic energy, which is equal to minus the divergence of the scalar field times a velocity vector. So plus I have rho times d by dt of p by rho. So that I transformed into dou p by dou t plus del dot pv, right? So now if I add equation 1 plus equation 2, so what happens? So rho can be taken common, so that becomes the d by dt of, so this is also differentiated with respect to time, this is also differentiated with respect to time, total derivative. So I can club them together, so that becomes E plus p by rho plus v square by 2, which is equal to minus divergence of pv plus dou p by dou t plus a divergence of pv. So now tell me, so these two can be cancelled, right? So what I am left with? So left hand side is equal to dou p by dou t, right? So now I am again posing a question. Can you, or does it ring a bell to you while looking at this term? What is this term? E plus p by rho plus v square by 2. What is the term? What is this term? It is internal energy plus pressure energy plus kinetic energy. What is this? That is total energy, right? Yeah. So let me go on to ask one more question. If you look at only this term, E plus P by rho, what is this? Recall from your thermodynamics. If you can recall, tell me what is that? E plus P by rho, or if you want to represent this, you can represent E plus PV. So specific volume. 1 by rho is specific volume. What is this? From your thermodynamics. This is nothing but an enthalpy, right? Yes or no? Right? So now see what I am left with. Rho d by dt of h plus v square by 2 is equal to dou p by dou t. So now, if you can recall, so whenever you defined a stagnation temperature or stagnation enthalpy, so you defined h plus v square by 2 is equal to constant, or that is equal to h naught, right? Along a streamline or for a uniform flow, you defined it for like everywhere. The total temperature is constant or total enthalpy is constant. That is how you define, right? If you have any differential equation to come to this form, say like d by dt of x is equal to something. Okay, so if x to be equal to constant, what should be the right hand side? When do you get a solution like this? When you have a right hand side which is equal to 0, then only you will get x is equal to constant as the solution for this differential equation, right? Yes or no? Yeah. So now tell me, if this has to be true, then what should be the assumption I should impose so that I can make this term is constant? Tell me, which engineering assumption can make this differential equation, the solution for this differential equation of this form, h plus v square by 2 is equal to constant? Steady flow, very good assumption. So if I make this to be a steady, so that means this term vanishes, becomes 0. So then my equation something looks like h plus v square by 2 is equal to constant, right? The solution for this differential equation. Clear? So this is a general solution, right? General solution for this particular equation. So let us say somewhere in the flow where velocity is 0 for this particular, or somewhere some boundary condition you apply where velocity is 0, then h becomes constant. So you call that as h naught. So this should satisfy everywhere wherever this equation is applied. So usually we took a given streamline, so it should be constant for a given streamline, right? So we call that as the stagnation enthalpy. Everybody clear? So the idea of stagnation properties comes from the energy equation. So it's a conservation of energy form. Clear? So now if I have to define this a stagnation enthalpy completely, then I have to say whenever a flow comes to rest adiabatically in a flow field where the, the flow field is steady, which is an adiabatic, which has no body force involved, and it is an inviscid flow field. Now viscous dissipation. So then if such a flow comes to rest, then the enthalpy or the temperature the flow would experience would be a stagnation temperature or stagnation enthalpy. Everybody clear with this a definition of stagnation temperature? Okay. So this is how we are actually going to deal in our actual classes. So like we will not just introduce you the term or terminology, we will try to bisect or do the postmortem of the given equation and see what are the hidden um, assumptions within the given equations, or what are the um, hidden mathematical meaning within the given equation. These kind of things like we will discuss. Like there are so many things we can discuss even within this slide, but so like for the purpose of demo class I am not going into the details of everything. So I just wanted to introduce you the concept of stagnation properties, because like the ramjet that kinds of deal with this energy equation only, the conservation of energy equation, the entire analysis. So I just introduced. So next few slides it might not be required, so it's just the same mathematical uh, substitution whatever we have done in the previous slide, that's given here. Okay, so this is also not required, the fruit for thought. We will discuss this in our actual session. So the idea here is like we kind of define what is a stagnation enthalpy is. So further if I also add, so I am dealing with calorically perfect gases, so I can always write H is nothing but Cp times T. So if H naught is constant, so that also means T naught is constant because Cp is already a constant. So this is a stagnation temperature definition. And more on mostly in our all the gas dynamics or the propulsion courses, we are going to deal with the ideal gases, we are not going to deal with the real gases. So we are good to go with these definitions. Everybody clear till this point? So let us jump on to see like the ramjet part. Total temperature and stagnation temperature are the same, so it's just the different terminologies, but representing a same quantity, physical quantity. Okay, so don't worry, so they are same. Okay, so yeah, this is fine. So these details are not required, and usually in our textbooks we are kind of seeing this particular form of a definition for total temperature, T plus C square by 2 Cp, where it is a local or a static temperature plus the dynamic temperature. That's how you define. So this is the form we use. But the thing is, this form is reduced. So it is nothing but an energy equation, right? H plus V square by 2 is equal to constant. So I can easily write it as Cpt plus V square by 2 is equal to H naught, or so H naught is Cpt naught. So, or if I take Cp common, so it cancels out, it becomes like this. So this form you are going to see, you are seeing here, right? So remember, whenever you see this particular definition, like immediately you should be able to recall that how you actually arrived to this particular form. So that is the point you have to catch. So that's why I spent some time on discussing that particular energy equation idea. Okay, So now, so let me just jump on to the relation, the isentropic relation, because this one we are going to use a lot in our jet propulsion classes. So that the T naught is what a stagnation temperature. Similarly, we can also define a P naught. So for this one, you have to add one more assumption, that is, you can define a stagnation pressure only when the flow is isentropic, whereas a stagnation temperature holds good even for adiabatic flow. But to have an idea of stagnation pressure that is defined, then you have to impose an isentropic assumption. The flow has to come to rest isentropically, okay, not just adiabatically. Whereas for T naught, still the flow comes to rest adiabatically, that is fine. Your stagnation temperature remains constant, whereas the total pressure to be constant, the flow has to come to rest on an isentropic fashion. Clear? So whenever the flow is isentropic, say if I'm taking any streamline, so point 1 and point 2, so I can always apply a isentropic relation between these two, point 1 to point 2, in this fashion. P2 by P1 is equal to T2 by T1 to the power of gamma by gamma minus 1. So it can be, you can also apply between total to static, or static to static, or total to total. It makes no sense because it's always going to be constant. Okay, so now, as long as you are treating an isentropic process, you can apply this relation, or else you cannot apply. Clear? You cannot simply apply between any 2 points which does not fall on the constant entropy line or constant entropy process. So this, again, this particular relation comes from thermodynamics, where if you guys can able to recall, you have written delta S is equal to Cp ln T2 by T1 minus R ln P2 by P1, right? So this is a famously known as TDS relations. This is again you are going to study in your thermodynamics. So that from there it is coming, because if it is constant entropy process, this term vanishes, it becomes 0. So you are left with Cp ln T2 by T1 is equal to R ln P2 by P1. So you can do the math, you can easily get it. So that becomes, if you equate it, T2 by T1 becomes P2 by P1 to the power of R by Cp. So you know Cp minus Cv is equal to R, or you can write 1 minus Cv by Cp is equal to R by Cp. So what is R by Cp? So we know gamma is nothing but Cp by Cv. So you can always write 1 minus 1 over gamma is equal to R by Cp, or it becomes gamma minus 1 by gamma is equal to R by Cp, right? So that's what you have here. So this gamma by gamma minus 1 factor comes from this particular relation. For all gases, calorically perfect or the real gases, whatever, so this relation always holds good. So this you have studied in your class 11th. So you should be able to recall that. Right? So this particular form of equation we use a lot, but always remember where to use and where not to use. That is where a student makes a mistake in their calculation. They apply this equation where it is not applicable. So maybe like 2 points where it is not falling exactly on isentropic process, then you cannot apply it. Adiabatic process is not an isentropic process, whereas isentropic process is adiabatic process. You can apply all adiabatic relations on isentropic process, but you cannot apply all isentropic relations on adiabatic processes. So that distinction you should be clear with. Okay. Okay. So now we will quickly see the ramjet analysis. The ramjet is perhaps the most simplest form of engine to deal with, at least in the pen and paper, but it is the most difficult form of the engine to design, because here we have no moving parts, all these things happens only the idea of our physical principles what we study in the textbooks, right? All pure gas dynamics ideas, pure physics. We are not going to put any kind of moving parts, motor or something like that to do the work done and all. So everything happens just by the flow transitions. Okay, so what we usually see in the ramjet is, like, we will have one intake section, we will have one combustion chamber, and we will have expanding nozzle. That's it. So we are going to deal with individual components and how it works, like intakes, how combustion chamber works or nozzle works in our actual classes. For the purpose of demo, I am not going to deal with like individual components here. So but see, simply we have an intake, that is a supersonic intake. What you see here, you see only this as the physical part, but this is not just the intake. The intake starts from here. So if you are able to see, so this intake should look something like this. So the imaginary line you are not able to see, but the thing here is, you have a uniform flow that is coming like this, and you draw an hypothetical boundary. So now you see, this is actually the area that is actually diverging, right? So that means, so this area over here to area over here is converging, right? The body is diverging, but the area is converging, right? So you have a more area over here and less area over here. So it's kind of a converging, and then again you have a diverging section, because this is increasing now area. So it is a converging diverging nozzle. So it is a supersonic nozzle. So what does that tell you? If you are dealing with the supersonic intake, what does that mean? So your ramjet operates on supersonic speeds, yes or no? If you are using a supersonic intake, that means it, it has to operate on a supersonic regime, right? And in your gas dynamics, you are going to study all about the supersonic duct flows. So like 1D duct or a converging diverging nozzles and all. So we are not going to deal those things in this demo session, but all those things you are going to be introduced. Okay, so now, so we will quickly do a analysis for this engine alone. So what do we have? We have a flow that is coming at some Mach number, say entry Mach number ME, with some mass flow rate m dot a, and a temperature here is say Ta. So like, let me call it as Mi, that is intake Mach number. Ta ambient condition, Pa the ambient pressure, the density is ambient density. The corresponding stagnation temperature, I can define it as T naught A. The corresponding stagnation pressure, I can define it as P naught A. So how this can be defined? We have T naught A is nothing but Ta plus Ci square divided by 2 Cp, or I can also write, so we can also always write a speed of sound as root of gamma RT for calorically perfect gases. So it can be shown as Ta plus Ci square divided by 2 times Cp can be written as gamma R divided by gamma minus 1. So if I take Ta common, so what happens? This becomes T naught A divided by Ta, that is equal to 1 plus gamma minus 1 by gamma minus 1 by 2 times Ci square divided by gamma RTA. So gamma RTA is nothing but A square. So Mach number, we have a Mach number definition, that is nothing but velocity divided by speed of sound. So we can always write it as ma square, right? So I'm not going into the details over here. So I'm just introducing the terminology, but in the actual sessions, we are going to see the details. Okay, it's like way before we enter this particular discussion, um, you might study these concepts in your gas dynamics, so it becomes much more easier for you guys to understand what we are dealing in these sessions. Okay, so now we have a form like this. Similarly, I can also write an exit Mach number to be ME, the exit temperatures to be TE, then exit total temperature to be T naught E. So I can write T naught E by TE to be equal to 1 plus gamma minus 1 by 2 times ME square. In general, this gamma and this gamma can be different. So I will write it as the gamma of gas, because what happens in combustion chamber, we introduce the fuel. So that means we are changing the properties of a gas. So the air properties and the gas properties can be different, completely different. So in general, gamma and gamma G can be different. Clear? So what is an ideal ramjet? So the ideal ramjet is one where your exit Mach number and incoming Mach number and the exit Mach numbers are same. So this is nothing but an ideal ramjet. So most probably in your gate, you are going to see a questions from ideal ramjet concept. Clear? What is ideal ramjet means?
Guys, do respond. Are you guys understanding? Mansa, Manu, Sheetal, Tushant, Rishon, Cynthia, Devnath, Bharat, others. Okay, thank you. Yeah, please continue.
Okay, yeah. So this is what ideal ramjet means. So like most of your gate questions comes from this particular idea of ideal ramjet. Okay, so the ideal ramjet does not necessarily mean your stagnation pressure is same. So they change. Stagnation temperature is same. No, they change. So but the ideal ramjet only means that your incoming Mach number and exit Mach numbers are same, not velocities, Mach numbers. Mach number is a non-dimensional quantity. You define it as local speed of the fluid to the local speed of sound. Okay, so that is how you define. So they are same. Mi is equal to me, the exit Mach number. So this is how we define. So this TS diagram I am not going to deal with, because to introduce you the TS diagram, I have to go to the jet propulsion cycle, ideal cycles and the actual cycle analysis. So then only you will get an idea of how to understand this TS diagram. Right now, I am not going to discuss in detail about the TS diagram. But remember, the ramjet, at least in pen and paper, is the simplest engine to analyze. In practice, it is very difficult to design. Okay. Okay, so let us just see how we typically analyze the ramjet engine. So what we have in the inlet, we have an adiabatic compression. So where you see all these points represent stagnation points. Okay, so you have T naught 1. From there, you are going to increase a pressure to, so like P naught 1 to P naught 2. Since it's an adiabatic compression, no energy being added or no energy being extracted. So in a sense, so no heat is being added or no heat is being extracted. So your total temperature remains constant. So T naught 1 is equal to T naught A, since it's an adiabatic. But P naught 1 is not equal to P naught A, because you can have a irreversible effects. So that will result in the losses. So that is why your total pressure is going to decrease. But still, the idea here is like you are going to increase the pressure from one point to the another point through a compression, that is a ram compression. Which pressure is increasing? The pressure which is increasing is a static pressure. So this is increasing, whereas a total pressure is decreasing, that is less than your P naught A, owing to irreversibilities. But what we are doing, when the flow is coming onto the engine, you don't exactly have a pressure that is P naught A. P naught A is the pressure if the flow comes to rest adiabatically. But it is not at rest, it is at a supersonic speed at some Mach number. So when you can ideally, if you can bring this flow to zero velocity, then this pressure should naturally, the local pressure what you have, PA, should naturally to increase to P1, that should be equal to P naught A in ideal scenarios, but it in actual scenarios it becomes P1 is equal to P naught 1, which is not equal to P naught A. Clear? So you are increasing the pressure by decelerating the flow in the inlet, so that when the flow comes to a combustion chamber, so like say like this is my ideal the schematic of a ramjet. So when the flow comes to a combustion chamber, you have decreased your velocity at mi is equal to some supersonic speed to very low subsonic speeds, nearly zero. Okay, so in the process what you are doing, your pressure over here Pa is now increased to P1. It is nearly equal to P naught A, not exactly but nearly. So you increase the pressure and decrease the velocity, and now what you are doing, you are adding the energy in the combustion chamber. The fuel burns, the energy will be added to the system, so that your temperature, the T naught 1 what you had here, will be increased to a new value T naught 2. So now this is now at a higher energy level because you are added the fuel, you are added energy. So this energy is now expanding in the nozzle, where again the reverse process happens. Here the flow has decreased, here the flow will increase. So while doing so, you are going to decrease the pressure while increasing the kinetic energy. So the T naught 2 is equal to exit total temperature, whereas P naught 2 is not equal to P naught 1 because you are adding the energy. So like in an um, ideal scenario, you want to do the combustion at a constant pressure, but in practice there will be a pressure loss. Let us treat, so there is no pressure loss, so then your P naught 1 is equal to P naught 2. Now the P naught 2 to the exit pressure PE, that is how you are expanding. So while doing so, the flow is accelerating and you are getting the thrust. Why? Because you are generating the momentum. Everybody clear how the ramjet operates? I understand if you are not able to catch the details, but that is fine because it is not a detailed class. But at least, are you guys able to get the essence, like how the ramjet works? Okay, so if that is the case, then it is very good. So let us just see one or two questions from previous year gate, and we can wind up this demo session. Okay, so yeah, so this is the analysis of a ramjet like that just I have shown. So in this slide you can also find it. So as I said, the inlet velocity should, sorry, Mach number should be equal to exit Mach number for an ideal ramjet. So we all know how to define the Mach number, that is velocity by speed of sound. So inlet velocity is Ci and inlet speed of sound is root of gamma r T1. Similarly, the exit speed of sound is the gamma g rg T exit, or the T4, whatever you want to represent, you can. So that's what I'm just substituting over here. So you can always recall these equations and you can proceed with the problems in your gate. But always remember the concept through which you are dealing with. These equations, like by the time once you start using it in multiple tests, mock tests, and many different places, this equation automatically um, comes to your mind. But only thing you have to focus mostly on is you have to focus on the concepts, where to use and where not to use. That is very, very important in propulsion or even gas dynamics in general. Okay, so clear. So shall we take one or two questions just to see like what type of questions you can expect from these concepts? Ready? Okay. So this is one question which is being asked in GATE 2013. See, which one of the following shows the correct variation of a stagnation temperature along the axis of an ideal ramjet engine? Can you guys tell me? I'll quickly give you a 30 seconds time. So we have a ramjet. Say this is my axis. So take any streamline. So all they are asking is like from here to here, that is an intake. So then we have a combustion chamber. Then we have a nozzle. Right. So now all they are asking is like how the stagnation temperature varies. So from here to here, it is an adiabatic process. What happens? It is constant, right? The T naught is constant. So in the combustion chamber, we are adding an energy, we are adding the heat. So the stagnation temperature has to increase. So T naught increases. And here to here, again, it's an adiabatic duct. So there again, T naught is constant. So which one is correct? Option B, right? So constant in intake, increase in combustion chamber, and again constant in nozzle. Right? So everybody clear? Shall we move to the next question? Okay. So this one is a numerical entry type, which is being asked in 2014. A cruise missile with an ideal ramjet engine is flying at a Mach number 4 at an altitude where the ambient temperature is 100 Kelvin. Consider the ratio of specific heat is equal to 1.4 and specific gas constant is 287 joules per kg per Kelvin. If the stagnation temperature in the combustion chamber is equal to 2310 Kelvin, the speed of the exhaust gases in meters per second is. So again, this is a straightforward question once we have done with our regular classes. So for today's classes, let me just give you an idea how to proceed with this question. So again, we have a ramjet engine. So we have an inlet condition where flow is coming at a supersonic speed, where ambient conditions are TA is 100 Kelvin, and we have a combustion chamber in which we are adding an energy. So at the exit of the combustion chamber, say we have T02, that is equal to 2310 Kelvin. Okay, so that's what they're saying, right? Stagnation temperature in the combustion chamber is equal to 2310 Kelvin. All they're asking is like, what is the velocity at the exit plane? Straightforward now. So they already mentioned it's an ideal ramjet. So what does it mean? So Mi is equal to M exit, or else Ci divided by root of gamma R Ta should be equal to Cj divided by root of gamma R Te. So now see, since they are mentioned, consider ratio of specific heats 1.4, gas constant 287 joules per kg Kelvin, and they did not mention anything other than that. So what we are going to treat here is So this gamma and R are same for both air and gases. So that means I can cancel these two out. So that simply gives me Cj is equal to Ci times root of Te by Ta. Straightforward. So only thing I should know here is what is Te and what is Ta or Ci. Ci we can easily calculate because the inlet Mach number is given to you, that is 4. So if Mi is equal to 4, so Mi is nothing but what? Ci divided by root of gamma or Ti or Ta. So that means, so from here I can calculate what is Ci. So Ci can be written as Mi times root of gamma or Ta. So I can replace over here. And similarly, Te, how do you calculate Te? See, I can write Ci is equal to Mi times root of gamma or Ta. Similarly, I can also write Cj is equal to Me times root of gamma or Te, right? Or this relation also you can use T naught E by Te is equal to T naught A divided by Ta. This also you can use. So from here also you can calculate what is Te, because T naught A by Ta you can easily calculate using the Mach number 1 plus gamma minus 1 by 2 times Ma square. So if you put it, so you can always calculate this ratio. So once you know this ratio, you can calculate what is Te. So because Te is nothing but T naught E times Ta by T naught A. So you can always calculate. So like I'm just showing the different approaches, how we can proceed. So let us try to solve this problem using this approach. So there are multiple approach you can always proceed with and get the same answer as long as you are doing it right. So now I have Te, that is equal to T naught E times Ta by T naught A, and T naught A by Ta can be written as 1 plus gamma is 1.4 minus 1.4 by 2, that is zero point 0.2 times inlet Mach number, that is 4 square. So if you use that one, you should be able to get this ratio as 4.2. So once you do that, so you can apply over here. What is T naught E? That is 2310 Kelvin divided by 1 4.2. So you should be able to get exit temperature. So you can get the exit temperature value and substitute back to get the Cj, because Mi is equal to Me. So Me is 4, 4 times. You can always get this one. That is one approach. The other approach would be simply an energy equation, because we know how to define T naught E. T naught E is nothing but Te plus Cj square divided by 2Cp, or I can write it for Cj. So that is going to be T naught E minus Te times 2Cp. So that is square root of 2Cp times T naught E minus Te, or I can write it as square root of 2Cp times T naught E times 1 minus Te by T naught E. So what is Te by T naught E? That is nothing but Ta by T naught A. So that we calculated 1 over 4.2. So you can always substitute over here and you can calculate again. So T naught E, you know, 2310. What is Cp? Gamma R divided by gamma minus 1. Both the information is given. So this is 1 over 4.2. So if you calculate, you should be able to get Cj equal to 1880.383 meters per second. So or else you can also do in this fashion. Once calculate Te from here, substitute back over here, you should be able to get the same answer. So everybody clear with the approach? Since it's a demo class, I don't expect you guys to get the numbers before me, but in actual classes These kind of questions you should be able to solve once we have done with our theory. And I know like you are going to solve. Clear? Any doubts so far from you guys? So like this is an end of our demo session. If you have any doubts, you can reach us at IIT and Gate classes. See, like in today's class, what happened, like I had to go through a ramjet as a simple concept, but you guys are able to find a difficulty in approaching these, right? You have to get to a multiple subjects first. Like you should be clear with your gas dynamics, you should be able to clear with your thermodynamics, right? The jet cycles, right? So all these
There is
things like
one
we have to
question.
study
Can
first.
you answer?
Yeah, I got it. Why we won't use a stagnation temperature in Mach number equation? So the question is like unclear to me. So do you think like, so what are you asking? Like you want to represent like this gamma T not something like that? Is this what you are intended to ask? So the idea is like you can always define a Mach number based on the stagnation temperature. There is nothing wrong with that. But I don't understand why do you have to use the Mach number in a stagnation condition? Because what exactly stagnation condition means? We already defined in the very beginning of the class, right? When the flow comes to rest, what happens? The velocity becomes zero. So the Mach number is nothing but V by A. So if V becomes zero, what is the point in defining a Mach number where a local velocity is zero? Does that answer your question? Yes or no? Okay, good. Yeah. So anybody else have any other questions? Okay, sir. So if they don't have any other question, that means like we can wind the session here.
So, guys, next session